been travelling in Australia, giving presentations in Cairns last week and in Townsville this week. I won't go through Carey's CV, but I would mention that he did work for 6 months at Antennas and Propagation for the CSIRO in Epping in 2005. So we do claim him as part Australian after that experience, I guess. I guess I should also mention too that the talk today is sponsored by the Antennas and Propagation Society, and one of the main features of the IEEE is that they're very good at disseminating technical information, and that of course comes in the way of periodicals and journals, which you all know, but it's also in terms of this distinguished lecturer tours that they support. So that brings international experts to other regions, and we're the beneficiary of that today with the talk. We haven't actually set up an Antennas and Propagation chapter in this section, but certainly something that we need to think about if we want to sort of attract more speakers such as Carey today. I won't say too much more. I'll just hand over to Carey. The topic today is modelling standoff radar scattering of concealed body-worn objects for suicide bomber detection. So very sort of topical topic, I think. Thank you.
Thanks, Graham. So it was 14 years ago that I came from my sabbatical to work at CSIRO. I had a marvelous time and had wanted to take every opportunity to come back to your wonderful country and see as much of it as I can. I haven't been to northern Australia, so this is my first time here. And let me say, I now have another place that I have to come back to in a few years out. It's always interesting going from northern hemisphere to southern hemisphere. Boston, of course, is fairly far north in the northern hemisphere of the United States. The weather in Boston is hot as summer right now. It's not actually cold here, even though it is your winter. But the main remarkable thing I find being sort of like, well, I don't know, is it horseshoe crabs that do solar navigation? I tend to look at where the sun is and determine where my bearings are. And in the southern hemisphere, the sun rises on the right and sets on the left. And like, what do you mean right and left? It's to the east, right? Except generally you look, well, the sun, unless you're right at the equator, the sun is sort of in the north, right? And so if you're sort of generally facing in the north, it comes up in the east, which is on the right, and sets on the left in the west. Whereas in the United States, it's just the opposite. So I expect the sun to go this way. And for you folks, that would be very strange. So, in any case, the topic for discussion today is basically long title, but I want to make a better airport personnel scanner, so that you don't. Well, I mean, as it is, you go through these detectors and they're very sophisticated microwave radar systems, and almost always you get patted down right after you go through. And it's sort of like, why are we doing this if it's just going to lead to well, invasive, well, I don't say humiliation, but penetrating your personal space, which nobody really likes. So I'm talking about what the challenges are and what my research has done to try to alleviate this. This is all sponsored by the Department of Homeland Security in the United States. Our center, see this actually works, ALERT, is acronym for Awareness and Localization of Explosives-Related Threats. So the concealed objects, well, these are concealed explosives. That's what we're trying to find. And indeed, the radar systems work pretty well at finding guns and knives, but blobs of material like an explosive don't have a particular pattern that you may want to try to look for, and so it makes the problem a little more challenging. So I'm going to talk about a little bit about the state of the art, what you go through when you go to the airport now. Multi-static radar, our blade beam reflector, which was a key piece of hardware that we're using for addressing this problem. The elliptical toroidal reflector, You can tell this is an antennas talk, although I'm not going to concentrate too much on antennas. Penetrable dielectric imaging, that is, dielectric is sort of the characterizing aspect of explosives, that is, guns and knives are metal, not very interesting dielectric, they're just perfect electric conductors, whereas penetrable dielectrics are more typical of TNT or RDX or explosives, and some of our experimental results. So this is the object that, or the portal that most of us have been through. Occasionally they're metal detectors, but the more advanced technology are these millimeter wave imagers. This is millimeter wave radar, 26 gigahertz plus or minus 3.5 gigahertz, so 7 gigahertz bandwidth. It's a portal that you stand in, you put your feet on the little yellow footprints, raise your hands over your head, wait for 3 seconds as it goes click, click. It does a pretty good job of finding everything or alerting on anomalies, everything that's not metallic as well as metallic. Everything that's not biological, everything that's not part of your body shows up. But that includes things that you may want to conceal that in fact are just perfectly innocent. If you have a money belt, for example, you have a bunch of cash, you might put on a belt under your shirt. You don't want everybody to see this. On the other hand, it's not particularly dangerous, so that's fine. If you have a medical device, if you are religious and you tape a Bible or the Quran to your back or your stomach, these are not particularly dangerous objects. And again, they're things that you may not want everybody to know about. There are a few limitations. There are dead spots in the imaging, and if I had security clearance, I wouldn't be able to talk about this, but because I don't, I can tell you, although I don't want to let the cat out of the bag, but certainly there are portions of the body that this doesn't do a very good job with. No chemical spectrographic information, which maybe IR sensing, spectrographic sensing might give you information on. Limited views, you have to be able to go into the box and out of the box, so you can't have sensors. I mean, there's no door that closes. They could have designed this with doors, but I think the passengers might have freaked out with that. Although it does occur to me that, I mean, it's much easier to scan full 360 if you have walls of sensors on all sides, and it seems that there is a precedence for this. Anytime you go through a revolving door, glass revolving door, you're in a box that's completely surrounded, and if you're just pushing, in fact, maybe putting your hands in front of you this way instead of that way would be okay. Oh well. I've mentioned this to DHS, and they hopefully they'll adapt it one of these days. Poor penetration through leather and metallic clothing. Most people don't have metallic clothing. I guess if you're a motorcycle guy, you might have leather pants. And if you're Lady Gaga and you have a dress made out of meat, definitely doesn't work. Also, this is definitely a surface detector. Anything that's internal, if you've swallowed a machete, it won't catch it. If you have surgically implanted explosives, which is a really horrible thought, but possibility, this won't detect it. Only stuff on the surface. So this is the paper from which everything was based. Dave Sheehan is a colleague of mine. We shared a PhD thesis or a master's thesis advisor. This is the image that you would get from the system, from a system that was published in 2001. It's 18-year-old technology. You'd think that perhaps things might have advanced a little bit, and they have, but it's turning it into products and making things actually fieldable takes a lot of effort. So this looks, I mean, frankly, it does look like an image. It's pretty impressive. Certainly you get curvature on the body, and you can see a lot of detail. Anybody pick out the gun right here? Not that hard to find. There's a second gun in his hand, not even concealed. So I mean, if you stare at these enough, you figure out what to look for in these, and they're not bad. Part of the problem, though, is that you want to see a human, so you project curvature, and so even though there's nothing here, you sort of expect the body to be moving around, being rounded, as it were. But if you put something there, or something over here, or maybe on the shoulders, certainly you can sort of interpolate, but if there's nothing, if it doesn't image, then maybe a foreign object there might actually disappear, which would be a problem. There's a few other issues. There are dihedral aspects. If you've done any synthetic aperture radar, you have trihedral fiducials, basically corner cubes, where if you send a beam, a radar beam, down at the fiducial, it bounces back as a retroreflector. Well, the space between your arm and your torso is a valley, so rays that hit the arm and then hit the torso, bounce back, look like, will have a strong response, and you see there's a line in here. Similarly, between the two legs, there's a line right there. This line is not a tail, it's not light shining from behind, it's an artifact. It shouldn't be there. There's nothing there. Why should this be as strong as the front of the thighs? Well, it's because of that dihedral artifact that is a result of monostatic radar. Further issue is, well, non-spectral dropouts, the lights, the beam that illuminates the shoulder, because it's tilted relative to the planar sort of flat chest, it's tilted and rays would end up going upwards rather than backwards, or back to the transceiver, and as a result it does seem to miss some of the stuff. Okay, just a quick primer on types of radar, multistatic versus monostatic. Monostatic, you transmit at a point and then receive at the same point. Use a transceiver, and in fact you probably use several of these, multi-monostatic. Each one of them is a separate device. No cabling or synchronization between the transmitter and receiver. They're both in one radar unit, and that's fine. The problem is it does lead to these dihedral artifacts. There's bistatic, where you have a separated transmitter and a receiver, and this gives you, well, it doesn't fall prey to the difficulty of the retroreflection and multi-bistatic. But the best is multistatic, where you might transmit through multiple transmitters and then receive from multiple receivers. The analogy here that I use for visitors to the lab who aren't particularly technical, we actually had Theresa May show up about 3 years ago visiting our lab, and trying to explain technical, electrical engineering stuff to a politician is But the way I tried with this was, suppose we wanted to characterize this room on a dark night, and each of us had a headlamp on our head, and we could do two different possibilities. One is each of us could come in separately, one at a time, to our assigned seats, and then turn that headlamp on and look all around, write notes, 3 chairs, and a column, projector, screen, and all that, and then leave and have the next person come in. That would be multi-monostatic. Alternatively, you have everybody come in at once, all turn their headlamps on, all look at everybody else's headlamp lighting. It'd be a lot more information, right? So multistatic really does give you a lot more, but instead of n observations, you have n squared observations. So it's a lot more data, it's a lot more processing, and frankly, to coordinate what one person sees from another person's light requires that cabling and in-depth knowledge of the relative positions of everybody. Okay, so other little quick radar aspects. The aperture here for either an antenna or an array. The size of the aperture relative to the range R gives you the range resolution, which is the speed of light divided by twice the bandwidth. If you have, this is sort of standard radar stuff, you have a very wide band signal, you have a short pulse. The short pulse isolates the spot. This is the spot of actually the point spread function of the antenna. And this controls the range in the range direction, how tight the spot is. The cross-range resolution is based on the aperture here. So this guy and that guy, clearly if you're farther away, the range resolution physically is not as tight, but it's proportional to distance and inversely proportional to the resolution cell is inversely proportional to D. So if you want higher resolution, you increase D or decrease wavelength lambda. Okay, so typical means of doing this, and this is maybe a little bit more detail than you need, but you could have a mirror that raster scans back and forth. You could have an electronically scanned phased array where you bounce by adjusting the phase from various points in here, you can focus on points in the target region, or you can have a synthetic aperture where you move a transmitter and a receiver back and forth, and from the various positions you synthesize a virtual aperture. All these are useful for identifying the high-resolution dots in the target space. Okay, so what's the big deal? How big a deal is a monostatic versus multistatic? Here we have a case where we have a V-shaped or corner-shaped piece, and we are looking at actually this is experimental results associated. Well, no, this is model results. So we observe, we transmit and receive or transceive various points along this arc. So we transmit and receive here, 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 these points. And it's supposed to look like this green object. In fact, it's just this little bright spot in the center. If you do multistatic, where you transmit just from one direction and receive along the blue, that is one transmitter, multiple receivers as opposed to multiple transceivers, notice you get something that lights up like this. And in fact, it images the corner as it's supposed to. So great. We're happy about that. Okay, so now different detection regimes or problems. If you could get a football field away with your detection, that'd be great. The problem is it's hard to get multiple views of the target. You want to be able to look at the left, the right, front, and maybe behind. And to do that on a target that's 100 yards away, you need a detector that's the size of a football stadium. A little expensive and impractical. You can do this much closer, maybe from the side of a truck, 3 to 10 meters. You might have a margin of safety in case the suicide bomber decides to blow himself up in that case. And you can also conceal things inside a truck. And this might be worthwhile or useful in, say, a parade type environment. People walking by, as they walk past the truck, you can sort of view and see what's going on. The airport security is inside this portal, like we saw with the L3 ProVision system. And of course, this is the easiest to observe from, because you can observe from the left and right and the top and all, approaching and leaving. So lots of different ways of sensing. Whereas this guy, you sort of get one shot, and this one you might just get one side of the person, but not the other. This is the one actually that we're going to concentrate on the most, because it's the richest electromagnetically. Next, what does the target look like? Well, we're going to look at humans, and humans are not perfect cylinders or ellipses. This is a cross-section of a human corpse. This was part of the National Institutes of Health Visible Human Project, where they froze corpses and sliced them in 1 millimeter sections. So if this looks sort of like pathology, it is. You can see the ribs in here. The yellow is a sort of fatty region. This is the spinal cord, the spinal column there. This, I guess, is upper arms. So this is the humerus up there. And we have, I think, most of this is liver, and there's some blood vessels and other stuff. In fact, we don't really care so much about what happens inside. The main thing we're interested in is just the skin on the outer layer, because skin is high water content tissue. At 30, 60, 90 gigahertz, we're talking wavelengths of the order of a millimeter, a few millimeters. 60 gigahertz in free space, it's 6 millimeters. So 1.4 millimeter thick skin, two-way travel time, especially when you have a dielectric constant of about 30. It's several wavelengths of attenuation. All you really care about is that outer surface. It doesn't really get to the inner surface much at all. So this is one of the reasons why this is a surface scanner as opposed to a volume X-ray type scanner. All right, so this is the innocent case. This is the threat case with 9 pipe bombs, just to sort of show what this might look like if you had pipe bombs. We have a lot of waves to worry about. So this is basically just a swan and a bunch of koi, but there are ripples on the water indicating that indeed there are a lot of ripples, a lot of complicated patterns. In fact, if we look at the patterns on here, you look very closely, you can see They're waves hitting the beach of the body, as it were. These are electromagnetic waves at 77 gigahertz, focusing in on just the front surface. Well, the front surface with targets. You can see that there's a lot of constructive interference relative to relatively smooth. And if we zoom in, you can see the interaction left and right, bouncing back and forth between the pipes. This looks like waves hitting a beach from an airplane. This looks, well, I don't know, looks pretty complicated. If we could put sensors right in there, certainly you could tell this if there are these four round circles or not, but we can't get right in there. In fact, we have to observe this from a distance. Okay. So in order to do this, we want a tight spot on the body. We have a custom designed elliptical system to allow multiple overlapping beams with focusing while being wide angle at the same time. We have multiple transmitters and multiple receivers to get the full 120 degrees from in front and 120 degrees in the back. We indeed believe very much in this multi-static transmit and receive arrays. So we have multiple transmitters. As it turns out, 7 transmitters and 151 receivers to avoid the dihedral artifact. And by the way, the dihedral artifact is lessened if you spread your legs a little bit, but there's certainly, you can imagine, lots of contours in the body where you can't eliminate just by assuming particular positions. Nothing else between your chin and your chest. I mean, there's a valley in there, so you really want to get rid of this if you can. All right, so our idea is to take a custom-built reflector that will produce a very thin illumination, just on an incident beam, just on a very narrow section of the body. By doing this, in fact, instead of being a raster scanned spot, it's a raster scanned vertical line across the body. And each line would be a two-dimensional inversion, so it produces this sort of two-dimensional view from above, where the bright colors are the reconstruction. This clearly looks like something sticking out. In fact, it is. And we stack these. So this guy was maybe this one, what is it? Maybe that guy right there. We take one above and a couple below, stack them all up, interpolate. We get this nice depth-based reconstruction. The white objects are white features are objects that are protruding. And in fact, the two protruding objects that were originally part of the body are well established and imaged. To do this, we have a custom designed blade beam system, this guy in here. And what it does is it's elliptical in the vertical plane and parabolic in the horizontal plane. And the advantage of that is that it produces a series of collimated, well, focused in the vertical direction, but collimated in the horizontal direction. So it produces a line focus along these three idealized human contours. What that does is it just lights up that section and nothing else, and as a result, anything that's outside that illuminated slice of body well, doesn't compromise or enter into the calculation. There's a little story about this fellow who was looking one night in a city street under a light, furiously trying to find something. His friend comes up and says, what's the matter? He said, well, I dropped my wallet here somewhere around here. And I said, well, let me help you find it. Is it right here, over here under the light? And he said, no, actually, I think I dropped it across the street. And why are you looking over here? He said, well, the light's better over here. Right? So the light's better right in there, but this then will the antenna will then be moved up for the next slice, and these will be combined. All right, there's one sort of technical geometric figure here. This is a tilted ellipse. The ellipse has one focus here, one focus there, semi-major axis A there, semi-minor axis B there. Not a very eccentric ellipse. And the idea is that it's tilted downward because we want want to put a feed point out of the way of the image point. So we image objects here. We feed our antenna there. This becomes a reflector right there. So the illuminated portion of the ellipse is this guy. Notice that the beams that are produced here focus down and don't run into the feed assembly region at all. This whole thing is then rotated about an axis Z right here and produces this shape stretched out into a circular toroidal object, surface, looking something like this. There's your axis of rotation, the feed point, the focal point, the image focal point, and because it's circularly symmetric, this guy turns into a focal arc. This, and any portion of this, depending upon, well, irrespective angle, looks pretty much the same. In fact, if you choose this point to be roughly half the distance from the center rotation of the circle, it turns out that it looks like, from that point of view, like a parabola. A little bit of high school geometry to turn your circle into a parabola. I guess it's high school calculus, getting the curvature of a parabola to find its osculating circle. Right, so this is our circle. We put the transmit point here. We illuminate this smaller section of the circle. It looks fairly parabolic, and it produces a focal line right along there. If we instead transmit at this point here off to the side, since it's symmetric, it looks very similar. 45 degrees off, it produces a line that's tilted like that. So from this point, well, actually 60 all the way to minus 60 degrees, you could get a bunch of these flat focal lines as seen from above. That's what the thing looks like in reality. We sliced it out with a computer-controlled milling machine. This is 4 sections of aluminum panel. Started off at each one of them, I believe, was about 40 kilograms. No, it was more than that. It was 80 kilograms. So each of these 4 was 80 kilograms. And now, with having removed, well, having cut the nice surface in the front, and also on the back, we've reduced it so it's 2 graduate students can lift all 4 bolted together. That's a toroidal reflector. The transmitter is in that card there. Receiver is positioned there. The target for imaging is sitting on our custom-built elevator. In fact, the target moves up and down because the target's much smaller than the reflector. But eventually, we will cast this reflector into fiberglass. It'll weigh of the order of 2 or 3 kilograms. It'll be easier to move than something that still right now weighs maybe 30 kilograms. A little heavy to move around. The view from the back, done to reduce the weight. Clearly, these are just rough sections of milling machine tool to remove space, remove unnecessary weight. About 90% of the aluminum ended up as dust. That's a lot of very heavy bags of dust. So. Yeah, we're down to 8 kilograms per panel at this point. All right, so this is the modeled illumination. Head-on is 0 degrees up to 45 degrees, as well as these are the focal position illumination. That's what it looks like on a human. And we would move the reflector up and down, and that looks a bit like scan the beam across a person, and because it's two-dimensional, a lot less information associated with that is you could find the contours you could cut and then combine the contours. So look at the metal box. This is measured data. This is model data. Pretty good agreement. This is an object, a metal chip on a duct, an air duct. Basically, we used a metal air duct as a simulant of human tissue. The idea being that humans are about 80% water. When it comes to dielectric constant, well, their reflectivity is about 70% that of perfect electric conductors. So we used an air duct that basically had a shape something like this, and then put a metal channel right there. Pretty easy to pick out, especially if I put the green mark on top of it. But beforehand, if you knew that the nominal shape was like this. So how do we get this guy, which is actually a lot easier to see? All right. This one here is a classic example of turning a bug into a feature. If you do computerized tomography, the back projection algorithm for CT scanning is the inverse radon transformation. It's actually filtered back projection. The rate of the accumulation of X-ray dose along lines from the transmitter to the photocell for an X-ray, in effect, is a radon transformation. It adds up the attenuation along each line from transmitter to receiver, as it were, without bending. To invert this, you do the inverse transform, but you have to filter it first, because otherwise you end up sort of, there's noise in the system that ends up sort of making the image blurry. So with the right filter, you get a very good reconstruction, which is great if you want a good CT scan of your body. But if you want to actually add a little bit of blur, I mean, here we have these striations, which are not detailed. They're just artifacts of our imaging. If we want to blur those out, well, we do the inverse radon transformation without the filter. So this is radon transform, inverse radon transform, no filter, and the net effect is it blurs everything. Now, this is a lot like a low-pass filter, except that it doesn't make it any wider this way or that way, and a low-pass filter will make it wider. It sort of sands down the edges, as it were. But the inverse radon it turned out to be a sort of very cute and quick way of taking stuff that has too much high-frequency noise, as it were, well, high spatial frequency variation, and smoothing it out and making it look like it, what you want to look at. Yes, please. Polarization? Yeah, so let's see if I get back to the actual one more. Yeah, this guy. So there are four, so there's one transmitter on here. There's a card with 4 transmitters there. The polarization is well, it's almost vertical. These guys are tilted towards the center position of that, but it is sort of vertically oriented, which things add up better this way than horizontal. So. Come on. There we go. Okay. All right. Next topic we want to look at here is so, you know, guns and knives, pretty easy to pick out. Dielectrics are a little bit more challenging. But they do have the aspect that waves traveling through a dielectric travel more slowly, which means that if you're looking at the time domain, that is, you send out a pulse and you time how long it takes to bounce off an object and come back. And if it's going through a dielectric slab, it may take a little bit longer. So whereas the nominal skin, it occurs after a few nanoseconds. This guy takes longer when you go through the dielectric slab, takes longer when you come back out again, and the delay there makes it look like it's further away. Well, it took longer, so it looks like it's further, the reflection off the back is further away. So in fact, if you have dielectric, you end up getting something that looks like a depression as opposed to a protrusion. This is a time domain response. You can certainly also do things if you have a focused spot, that is, you have a raster scan spot. So you have maybe focusing aperture, you have refraction occurring at the edge of the dielectric slab. This actually makes it look as if instead of focusing at this point down here, that's actually focusing a little bit above that. Both of these are in effect the same effect. They can both be used for determining both the thickness and the dielectric constant of the slab, assuming it's penetrable, assuming you can get some signal out of the back reflection. This is actual data from, in fact, from the ProVision system. This is is a torso. It's a little noisy, a little hard to see what's going on. Of course, it helps if you get multiple views. So let's rotate it back and forth and see if you can see an object. And you see the object that's sort of affixed to the upper part of the chest there. Let me draw your attention to this portion right in here. I'll play it again. It does look sort of like a depression. Again, you have to sort of have seen these before it stands out. For me, I can't see anything except that, but you can get used to this eventually. So this is a bottle filled with corn oil, I believe. Actually, the people who did this for us didn't tell us exactly what it is, but it probably is corn oil. It's probably not a bottle filled with TNT, but corn oil has a comparable dielectric constant to high explosives. And one thing about the high explosives TNT and RDX and PETN and HMTP are all relatively non-polar molecules, and as such have dielectric constants of around 3, very low loss, low dielectric constant. So these can be modeled with wax or plastics or, well, yeah, mostly waxes and plastics. Okay, so how does this actually work? This is a simulation showing us we have a dielectric object 4 centimeters high sitting on top of a background that's skin. Another object, the same material, 2 centimeters high. And what's the response from that? Well, looking at radar coming from above, so that is coming down this way and bouncing back, the response here images to this part, this in here images to the part in the middle, this in here images here. These guys are the signature of that object. These guys are the signature of this object. The 4 centimeter corresponds to basically the separation between the nominal response and the front surface. This guy is that back surface that as it goes through takes longer. It does reflect, but it takes longer to come through, so it images to a depressed portion. If it's half as big, it's imaged half as deep. Makes sense. And our observables are the delay corresponding, or the distance corresponding to the object, and the distance corresponding to the delay from the back response, back wall response. And the formula, the estimated formula for the dielectric, relative dielectric constant is 1 plus d delay over d object quantity squared. Notice if you just sort of grab from this figure what these guys are, it turns out that this is about 3 centimeters, that's about 4 centimeters. We throw this in, we get 49/16, 3. Well, 6% error. That's pretty good. We got a patent for this years ago on this. So there's a piece of beeswax with a little bit of titanium dioxide to control the conductivity, sitting on a piece of metal. It images out to this thing, which certainly looks like a depression. It's pretty clear, the right place, right height, and location. Right. Okay. So here we have an air duct with the dielectric simulant, TNT simulant, and a metal channel, and we look at the cut through across here, that cut cross section. We have nominal curvature of the air duct. There's this protrusion corresponding to that guy, and then there's this depression corresponding to that guy. And in fact, when we stack these, the hardest part of this actually is getting the graphics to look like it's supposed to. This is the protrusion, this guy in here, and here that corresponds to that guy. This is the depression, and you can pretty much pick those out. So, okay. All right, the last thing that I want to chat about here is a hallway-based system. What we'd all like to have, rather than a portal system where we have to go in and assume a particular pose and put our arms above our heads. By the way, when I do this, I invariably put my arms too close to my head like this, which produces a dihedral reflection right in there, which always alerts the, so I have 30 or 40 yellow rectangles all on my face, and the security guy sort of grabs at my hair, something under your toupee, or don't have a toupee. short sleeves, where are all these responses coming from? Anyway, we all prefer to not assume a particular position. If we could just walk by a detector, wouldn't that be great? The problem is, if you want to image this person like this, and make sure you get not just the portion that might be facing an array here, but also his front, his back, and maybe the other side. Certainly you could put a detector on the hallway detector on the other side between two panels. But the problem is, as you walk, the middle of your chest and the middle of your back, rays that would come from the side end up leaving and not returning in the direction that that you expect. So certainly imaging this point, any of these rays hit this guy and bounce back, no problem. Basically obeying sort of centered around normal to the surface. For this guy here, if we want to look at the normal, the portion that is about the normal to that point, notice how big this detector array has to be to have the same angle and same resolution. So this requires a gigantic array, and on top of that, this declining effect of sensors across here are in glancing incidents, really having a tough time illuminating that guy. So it becomes very tough to be able to illuminate, certainly to illuminate the middle of someone's chest. It's going to take an infinitely long array, not too practical for hustling for space. So the idea, let me make sure I get that right. Okay. So the idea is that if the subject is moving between left and right panels, then you have to put transmitters on both sides, that is all these red dots. You have to have receivers on both sides. And most importantly, you have to be able to transmit on one side and receive on both the side that the transmitter is on, but also on the other side. That's actually very important. So if you do that, then we have a detector array down here, a detector array down there. We get this guy, we get that guy, we get this one, which is beginning to get a little hard to expect stuff coming back. But if you put detectors on the other side, the rays the rays that speculatively would bounce off continue to the other detector. And the advantage of that is that you can basically see the front of the subject and the back of the subject, as long as there's cooperation between transmitters on one side, receivers on both sides, and transmitters on the other side, receivers on both sides. A lot of cabling back and forth across the top, but that's what you got to do. We got the patent for this idea about two months ago. Not really all that complicated. You can get patents for all sorts of ridiculous things. It's amazing that the patent for walking down a hallway and having the left side look at the right side, but from the point of view of security scanning systems, you need it, and people who adapt this have gotten rich yet, but we're hoping for it. So how does this actually work? In particular, let's take an actual cross-section of a body. This is the front of the torso, back of the torso, left arm, right arm, person walking in this direction. So the transmitters are in green, and receivers, we're just receiving, for this example, along the top, well, the left portion of the hallway. There would be a similar one down below, but there are too many lines as it is. So this transmitter illuminates the arm. It bounces off and is picked up by that receiver. This guy, here's the front of the arm. This doesn't necessarily all happen in the same chronological direction. This guy here gets one other part of the arm, fine. This one illuminates the middle portion of the chest, bounces off speculatively, is picked up on the other receiver. This guy, another portion of the chest, picked up, and finally the back is imaged. The net effect is that we get all these nice contours, the dark signals indicating imaged response. And if you put it all together, you know, add all these things, the entire left side of the body, as well as the front and the back, are pretty well imaged with the receivers up there. Do the same thing with you get a full 360 image. And yeah, so provisional patent, I have to update this because the patent actually was granted recently. Okay, so I want to talk for 45 minutes to make sure there's time for questions, but my conclusions here are that wanted to extend this idea of an elliptical torus that would illuminate just a narrow portion of the body with multiple overlapping, high-quality, high-gain beams that could concentrate on each cross-section at a time, and then have them stacked up to produce the image of the human that we're looking at. We've built it, tested it, optimized it. It's set at 60 gigahertz, plus or minus 3.5 gigahertz, so from 56.5 to 63.5 gigahertz. There are chips available that are actually about $200 for transmitters, receivers. We started off looking at, Raytheon could provide radars for $250,000, a little expensive. The Fraunhofer Institute in Germany could do this for $25,000. Actually, it was special for us that day for just $12,000. Until we actually tried to buy it and then realized that it was import controlled for Germany, controlled transfer to the United States, which was eye-opening. But it turns out that IBM designed this chip that sold it to Hittite, which analog devices. $200 a wideband transmitter receiver, separated transmitter receiver modules, and you put a reference line between the two and compare the channel through the air with the channel through the reference. It's a radar. They didn't actually believe it, so we applied for a patent on that as well. And it works. Yeah. Okay, so reflector antenna, 2D stacked reconstruction, fast inversion, and because it's multi-static, not a lot of dihedrals, we can image corners as they're supposed to be, and taking advantage of advanced visualization. Using the depth information, we can figure out things like dielectric constant of foreign objects. With that, again, I want to thank Homeland Security for supporting this work, and that concludes my talk. Questions, please. Yes, sir. Yes. So all right. This is another 1 hour lecture at this point. If you're using a synthetic aperture, you sort of have a moving antenna, and you want the target to stay stationary. If the target moves as well as the antenna, then not only is there blur, but there's sort of a decoherence of the observation of one set of the information taken at one position of the antenna versus another position of the antenna. That's one of the issues with this moving L3 ProVision system. If you move while you're being scanned, if while you're here you hiccup or sneeze, which I tend to do a lot also, it fills the image with artifacts. So yeah, it does end up leading to some issues. Now, if you instead have a raster scan system where you electronically or physically with a big mirror or lens or reflect array of some sophisticated system antenna produce just a spot and then move that spot back and forth, well, you might blur the person as the person's moving, but each spot produces an image. That is, that spot at that point gives that reflectivity in XYZ space, and that's correct. So from the point of view of having a person move, you really have to either do things, you have to have a filled array and instantaneously grab information from everywhere. And there are a lot of, I mean, if you're talking, 60 gigahertz with 5 millimeter wavelength, there are an awful lot of transmitters and receivers that you have to have sort of talking to one another. Certainly you can do this quickly, but you can't really do it sequentially. That is, you can't look at receiver 1, receiver 2, receiver 3, receiver 10,000. I mean, yeah, speed of light goes pretty fast, but the 10,000 of these operations, it starts taking more than 200 milliseconds, and then a subject moving will lose, that is, you won't get the whole object in the whole subject behaving as if it were stationary. I mean, of course, we're never stationary. In fact, usually we use metal ducts rather than graduate students as subject, is because it takes a few seconds to do this, and you can't stop breathing for 30 seconds. Well, I guess you could for 30 seconds, but heartbeats and just shifting a little bit. It's very tough to stay really steady. That's why the scan takes 3 seconds. They worked very hard to get that to three seconds to slide across that. And even so, if you hiccup, it can throw things off. But yeah, so the bottom line is, in order to do this hallway system, you have to have a full dense array, not a moving array or not a synthetic array. It just has to be filled with 10,000 transmitters and receivers. And even at $200, 10,000 of them tends to add up. So that's why it's still a wish list rather than an actual, well, not implemented. Yeah, so if the target were moving specifically, that is in a way that you were aware of and you could calibrate, then yes, indeed, that would be that'd be valuable. The problem is people move at different velocities and different parts, and as you're walking, if you're standing still and sort of moving along without your legs moving, that's fine. But if you advance your left leg and then your right leg and your left arm, there's a lot of different motion that's involved. If you were just rotating, that would be okay. But in a lot of these things, you don't want to have a circumstance where it requires too much compliance from the passenger. There's the Echo system had a focus raster scan spot. They had a panel here, and you have to actually turn around. Well, this is, I guess you could have a rotating platform, but I'm sure Grandma wouldn't be very happy with that, or the kids. Or if you're a terrorist, you might sort of try to mess it up, and so it's hard to have something that requires a lot of compliance. So indeed, motion could be helpful, but you have to, sort of paralyze somebody stereotactically for 3 seconds and then let them move.
Would it be possible to correlate like your radar with another type of imaging, like even
a LiDAR thing? Yep.
Or
yes.
even a lower frequency radar to give you basic position and then correlate it with.
Absolutely, and that's the active research in that, certainly. Yeah.
The question that comes to me is there's a lot of really hard work being put into it, and it's mind-boggling, but I want to approach it from the basis of facial recognition software that exists in general industry and other places, because it's all the same stuff, just different wavelengths we're dealing with.
Mm-hmm.
Okay, light stuff. I don't need a bucket load of sensors and that sort of things. One eye and blow the light around the place that you start naked, I'll pick up the artifacts that you're wearing. I can't see them through your clothes, and I guess that's why we're dealing with
That's right. Yeah.
frequencies. But I can do all this off basically a single.
Sure. The retinal scan or facial recognition. Absolutely right.
Artificial intelligence to look at it and say, well, that's a normal human being. Not carrying a salami.
Well, so you're saying you can look at somebody and decide if he's a bad guy or a good guy.
Well, if they were, which the radar, the high frequency
Yeah.
radio waves make them appear naked, basically. So you've got a little bit less resolution and light frequency.
Yeah.
But yeah, I could look at you with the eyes and tell what you've got on. And if it was approached from an AI perspective, a smart computer could be trained to sit there and just look.
Well, so but you're saying that it's hard to effectively conceal threats. Can you look at somebody? Well, can you look at a federal agent and realize that he's packing a revolver?
If he's naked, yeah.
Yeah.
Which is effectively what the
What the radar does, because it penetrates clothing.
that you're doing does.
Right.
So, yeah, in answer to the question, you can't tell the good guys from the bad guys, but you can tell the fact that he's packing one.
Well, actually, they're very good at concealing stuff. Let me give you a little story on this. The former TSA administrator, the Transportation Security Administration head, was a former FBI guy, and I guess he'll say, once you're FBI, you're always FBI, and if you're FBI in the United States, you're allowed to carry firearms concealed anywhere you want. This guy visited our lab and mentioned that he usually does carry a firearm. He didn't show it. I couldn't tell. And he's wearing a black suit, and he never unbuttoned it. He probably had a weapon on him. I don't know. I couldn't tell. I mean, his jacket was tailored nicely enough, so he's not naked. That's right. But one thing we did do was we used a LiDAR system for looking at well, basically if you use optical sensing to determine the envelope of the person, basically where all his clothing is, then you can sense with microwaves and millimeter waves inside that envelope, and it reduces the search space and saves a lot of computational time. We used actually we used a Kinect game, PlayStation, or I guess it's Xbox, where so when you wave your hand, it pretends like you've got a tennis racket or whatever. Game stuff. So it sends out structured light and interprets your motions based on this. Gives you a three-dimensional point cloud of positions. We use this for this fellow. His name's Pistol. I guess when you're born with a name like that, maybe you become an FBI agent. But Pistol. Anyway, we sent him a bunch of pictures that we've taken of everybody in the meeting, including pictures of him, and asked for permission to use this for our promotional literature and the annual report and that sort of stuff. And the response came back saying yes to all the photographs, but not to the structured light three-dimensional loaf picture. And I said, well, why? I mean, this doesn't even look like him. Why would he care about this? And I'm looking at it on retrospect very carefully. There was when you showed depth, color-coded, there was definitely a bulge right on the side of his body. And because it was a black suit, there were no shadows. And I couldn't tell, but it was very clear that there was a lump right here with the depth view that was in that. And I think that's probably why they didn't want it to because otherwise it's just a bunch of red and blue lines, and you can't recognize who it is. But anyway, the bottom line is that concealing can be done pretty well. Harder in Queensland where it's warm and you don't wear a lot of layers, but if you're in Boston where you've got a coat and a jacket and a t-shirt and lots of stuff, or you're wearing something very baggy, I mean maybe a sweatshirt, there are a lot of ways of concealing. I mean, I don't have any examples, but I've seen instances where it's like, geez, he's got that big a gun under his jacket. How can he possibly fit that without any bulges? But it can be done.
Yeah, I guess my thinking was using intrusive clothing
Yeah.
to make the subject appear a little bit on the face of them.
So pick your frequency. I mean, go from 2 gigahertz up to 120 gigahertz.
Well, it's the presumption that the frequencies that you would make people appear.
Yeah. Pretty much. Yeah, that's the deal. And it is also another interesting thing that the engineers work harder and harder to have a clearer and cleaner image of from what you're imaging. And when it gets to be too good, then all of a sudden it's like the people you're taking images of say, wait a second, it's too good. Back down a little bit, fuzzy. Make it fuzzy, make it cartoon character type stuff, put yellow boxes instead of real images. So it's, yeah, unfortunate. But. Other questions? Thanks for coming. We have not looked at polarization as an indicator. I'm thinking that, I mean, we did at one point, maybe a decade ago, consider it for targets that would have a specific orientation. Sort of, it'd be hard to put pipes on your body this way, but you can wear pipes this way. So if you transmit at 45 and receive at minus 45, then something that's lined up this way certainly becomes much more dominant than just random variations in the body. So polarization might have been useful there. For most of the imaging stuff, we sort of transmit on one polarization and just look at that polarization. The next generation of scanners would probably be left-hand circular. Well, actually, I guess they do. They set it up so that you receive on or transmit on right hand and receive on left hand, so that single bounces are captured, whereas double bounces, 1, 2, are rejected. That's one way of getting around the dihedral aspect. Of course, it enhances trihedral responses, and it also requires a bistatic system rather than a monostatic. That is, you have to have separate left hand and right hand antennas next to one another. But it's I mean, it's a way of addressing the main problem of dihedral bounce. Sir. So there's not a lot of computation, because the main thing is you have to think about it in terms of the time domain to get. Actually, I guess we analyze. If you look at the FMCW, then a lot of the calculation that's frequency modulated continuous wave radar, then a lot of the processing is done sort of at the front end of the radar system. We use step frequency, and for us, we need just amplitude and phase at each of a bunch of frequencies, which comes sort of right out of the demodulator. That's not too much. And then to combine these, well, I mean, they're 15 frequencies, or well, I guess no, we use about 45, maybe 50 frequencies. So for each scan, there are about 50 frequencies of processing. When you're talking 50 of stuff, it's not, 500,000 is a lot of computation. This doesn't require sort of inverting matrices or anything of that sort. The real computational load, or the real delay, is there's a lot of data, and just sort of transmitting the data from the digital, the A to D, getting the A to D to dump out the data, to store it optimally as a big block of data, then transmit to the computer. For whatever reason, that seems to be the real slowest aspect. So the actual computation is not too bad, but the data transfer is a slow weak link. You just need more computers, I guess. The computer scientists will always say, just more computers. Yeah.
That's a fascinating topic. I think if you're limited by frequency too, you think as you get higher frequencies, then you're going to get better resolution, and that makes it easier to detect smaller objects. But anyhow, very interesting talk. Mike, thank you for your time.
Oh, thanks for inviting me.
Yeah.
Appreciate it.
Appreciate you.
Yeah. Thank you. Okay.